Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about DDR5. So let's dive right into it. Now, first, exactly we have to understand what we are talking about. We are talking about basically next generation of RAM is here. Basically, how we went from DDR1 to DDR2 to 3 to 4 to 5. This is to DDR5. Now, in simplest term, you just take everything that DDR4 has and you double that puppy. That's all happened here. Now, there were key focus, like basically whoever, be it Macron, be it the whole association of RAM, they sat down is like what are the core focus for improvement. Right now, the primary focus of improvement is power efficiency, meaning for laptops and mobile phones, it should allow you to run for longer. That's first focus. Second focus is architecture refinement, because at this point in time we are in terms of horsepower, we are there. We are like we got it as much as we need. What we need to do is more efficient use of it. Basically think of this way, like you have the horsepower, you can have a car that has like 5,000 horsepower, or you can have a what we call a railway locomotive that has 5,000. Railway will do far more with that 5,000. So that's the one thing you have to understand. We are basically have to improve architecturally wise, meaning you have to be efficient with it. Then much higher capacity, because capacity is one thing that we are consuming like there is no tomorrow, and it will be the next workhorse for upcoming few years, so to say, hopefully. So first biggest change that you will notice is this puppy, that is PMIC, Power Management Integrated Chip. Now this puppy is there for power management because, well, power is the key to efficiency. The better power efficient you are, the less heat you produce, the less heat removal system you need. So this is one thing that you have to do. So how does this differ from old generation? Biggest change is motherboard will now only feed that puppy 5 volts. Now as you can understand, in voltage and voltage and amps relationship, the higher the voltage, lower the amp for the same amount of wattage. So even if you are consuming, let's say, older system had to provide 1.5 volts. Now this puppy will provide 5 volts. So even if it's consuming twice as power, from a motherboard trace layout point of view, it's generating less heat. So 5 volt is very good for the motherboard point of view, and they will only provide 5 volt. You take the 5 volt, of course, within this amp range, and go YOLO on it. I don't have to do anything other than that. So that's really good from motherboard manufacturing point of view, and it will allow basically RAM PMIC to step it down. Now you could have right now our current method is you have a power envelope from motherboard manufacturer, because again they have to design it, so they create an envelope like this is the lowest we can go, this is the highest we can go YOLO on it. And again, if you go above it, it could create unnecessary power draw, reducing system stability, or if you go below it, it could also create issue of overheating or frying something that was not. So power management, if it is directly done on the chip, it knows the board basically. So this has the advantage that it can be programmed properly by the manufacturer to be optimally serving this puppy, meaning it's like I got this, like I know this many chips, I know this IC, I know this package, and how to well serve it. So that's the main benefit. This will be very fine-tuned rather than working inside the envelope. It's like I got the main line, I will provide the perfect optimum scenario for this. Now you may be like, okay, what's the difference between 1.2 volt to 1.5 volt? Not for us, but for ICs, that's a very big difference. Especially think of this, let's say somebody creates a very energy efficient stacks, but it requires to go down to, let's say, 0.9 volt. Again, in older system it may create an issue, but if you have IC here, it's like I got this, I can manage it. Or something, let's say you put a RGB system in here, it's drawing more current, it will like I got this, I can still manage it. And that's why whenever you look at computer equipments, you will always find it has 4 digits after decimal point. So it will be like not 1.1 volt, it will be like 1.1327. It's like it can go down to that resolution, it has to. So to optimally use power provided by the motherboard, the onboard system is the best use case scenario, because every manufacturer will optimize it for the exact board. So if you have let's say Morbius system, or Aurora system, or Vengeance system, with all of them will know this is exactly how my RAMs like to be cooked. So they will be like, this is how much power we're gonna provide. So that's the whole point. And it will be better power management, because you could have some RAM that only has 16 GB. Of course, power requirement will be different compared to 32 GB. Or sometimes you could have 32 GB and 32 GB ludicrously fast speed, 32 GB with next level RGB. All those sort of scenario will be managed by PMIC. So it should yield into a bit more efficient improvements, utilization of RAM. what about the architecture? Now, in terms of architecture, just double everything. So improvement went from 64 GB, which I'm not sure did anybody actually bought 64 GB kit. It was ludicrously expensive. So DDR4, that is the maximum that you can have, will go to 128. So significant enough upgrade. And each stick will have two sub channel. Be mindful, it's still not like, technically dual channel, but each channel has two sub channel inside it. That's why you will see 32-bit main channels here. So older system is 64-bit. Now you will like, okay, rather than adding like, 264-bit, why the heck they reduced it to 32-bit? Well, that's the whole point. They want latency. Basically, the bigger the pipe, the more chunky data it has to send to utilize that pipe. Otherwise, what's the point of that pipe? But RAM is slow compared to processors. Processors are ludicrously fast. So processor could be like, hey, I want that file, and it's like by the time RAM is going there, taking it out from the chip, putting it to buffer stack memory, then trying to flush it to the CPU, it's like, nah bro, I want something else. That creates latency issue. So having two smaller pipes is far more efficient. So CPU can switch as much as that it wants, and this puppy can feed it without any issue. Now you may notice why the heck this image says 40 bits when I'm saying it's 32-bit. Well, there are extra bits for error correction if company wants to utilize that. Now burst length has been upgraded significantly from 8-bit to 16-bit. Now that means basically chunk of data is now much bigger. Benefit of this chunk of data, meaning the CPU can be fed very efficiently, very quickly. Now, what does that mean? For you and me, nothing. For application developments, not really that much. For CPU manufacturer, a lot. Basically, when we went from DDR3 to DDR4, there was not that big of a wow factor. However, slowly over time, it started to come in. But AMD Ryzen started to truly flex its wing because it was designed in such a way that it can truly utilize high-speed RAM. So if you had Intel system and AMD system had really good RAM, you will show it. And if you use the same RAM that was making AMD going crazy, you take the same RAM, put it in Intel, it was like, okay, like AMD could utilize that system. So next generation CPU will utilize that. It's not something that we will feel, but over time with next generation CPUs, that 8-bit to 16-bit, the fact that every single RAM stick is now inherently almost dual channel, it will allow CPUs to flex its wing. It's like, I got this. CPU, if it can rely on RAM far more readily, whereas I got this. Even if I change my mind, even it has what we call prediction tree. It predicts it, but sometimes it happens. You predict something wrong, then you have to change it. It's like, hey, I got the channel. I got this channel was preoccupied. It's like, okay, no problem. I will use the second channel. That's awesome. So this sort of architectural improvement should allow, basically megabits per second to go up, error rates to go down, latency to improve. All that thing should happen. And right now, many mobile phones from Samsung, flagship one, already have DDR5 simply because Samsung is one of the largest, semiconductor manufacturers. So they can just phone call it mobile division, bro, give us RAM. It's like, okay. So architectural improvement, that's the whole point. Basically, it's just trying to be more efficient. So one spicy topic is on-die ECC. Now let me be very clear about it. It does not classify as what we call mainline ECC. What does that mean? Simply means your data is safe when it's in the chip. That's awesome. That's great. But when you are transiting it, basically taking the data away, directly away from the chip and sending it through the whole pipeline to the processor, during this time data can flip. Now it's like, wait a minute. What? Yeah, that happens. Data flip is not locked or limited to directly happening in the chip. It can also happen during transit, and especially in a hotter environment, it goes up. Like you have two reasons why data can flip: A, thermal reasons; B, cosmic ray reason. So over time, if you have ludicrously large data set, it will happen. It's not like, oh, it may happen. It will happen. If you have large enough data set, it will happen. It's something like for a PC use, it's not a big issue. But for stability point of view, it's a very critical thing. So that's why we have ECC pipeline. Now, why the heck we have this on-die ECC when it's not a complete system? It makes manufacturing the chip much easier, because every time you manufacture a chip and you make it denser and denser, your error rate goes up, 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 up. Think of it this way, like Intel is such a large manufacturer and such a competent manufacturer, and yet they had such a hard time going from 10 nanometer to 7 nanometer to 5 nanometer. Why? Because every time you shrink it, your error rate goes up exponentially more. So you may have a scenario where you have a die that is like, hey, I'm gonna feed it 100 bits of data. Can it store that 100 bit reliably? Answer, no. So what does on-die ECC does? It takes care of it. So even if your chip is not up to the mark, the on-die ECC will be like, I got this, I will take care of it. It may not be the highest performing system, but it's like on-die system would be like, I got it. And over time, every chip degrades. Sooner or later, every chip degrades, especially in server environments, it will degrade. So if you have from day one on-die ECC, that's like, I got this. Over time, every chip will use it. The defective chips will use it from day one. And that's the benefit of higher yields, meaning each silicon wafer will have much higher yield. So that's why companies really wanted to have this on-die ECC. Now, is it helpful for reliability point of view? Little bit, yes, but not completely. Basically, servers will still not use this. Now you're like, why? Well, you need whole pipeline. Basically, you need ECC CPU. That's why there is a ECC CPU. You need motherboard. That's why there you have ECC supported motherboards. Then you have RAM. Only if all three things are there, then only CPU can have extreme high confidence. It's like, I sent the data went it correctly, and I retrieved the data is still not tampered. On-die ECC only guarantees that in the chip it will not be messed up. When you are transiting it, what's the point if you corrupt it? So why the heck company is doing it? When you have on-die ECC, it wouldn't be that complex. And not to mention AMD, because of the fact that they were like upcoming, they unlocked the feature of ECC on every system. ECC is one of those things that almost all CPUs have it, but companies like Intel block that function, and they're like, you have to buy K series to unlock it. It's like, bro, it's there. Like, I can take an electron microscope and see it. You just uploaded a microcode into it to block it. So it's one of those things that's like, we had the technology, we just never use it. Now there is one serious con with this. Now, ECC has hard lock specification, meaning it's the same thing when you have server processors, they're running much slower. It's like, why the heck a server processor is like 4.5 gigahertz when the same SKU can be in 5 gigahertz in desktop environment? Because the desktop environment is not running 24/7 into 365 until the day it dies. But, supercomputer systems or server enterprise, it is expected to run like that. So validation is much critical. At that point in time, it's like company has to validate that. It's like, no, I'm saying this will run at 4.5 gigahertz, meaning it will run at 4.5 gigahertz until the day it's like, it craps out. So for that, validation is expensive process, and higher the speed, the validation becomes more and more critical, and more things you have to throw away, because higher the speed, the validation starts to fail more and more things. So if ECC was made into an absolute standard, meaning all systems will have ECC, DDR5 will have ECC, it will get spec locked, and it will not get too much benchmarking. But from a stability point of view, it will be a GG thing. And I think we should have actually done that, rather than relying on some poor translation of on-die ECC to actual ECC, because I will explain why this. Because it will limit the processing speed, it will limit the horsepower from your RAM, but we don't need that much horsepower from RAM. I'll explain it further. So the first question is, should you buy it or not? Well, simple answer, if you can afford it, just buy it. There is no thinking about it. It's like, if you can afford it, buy it. Simply because right now, yes, you will be paying what we call early adopter tax, but it's a long-term investment, especially for people who use their computers for long durations. I mean, many things longer than 5 years, because after 5 years or 6 years, you may want to use your computer for something else. Let's say making a security server, making a NAS unit, making a router, all those jazz, and you will find out, hey, what if I increase the RAM to get more performance? Yes, deal. Oh, RAM, I have to buy it from a museum. That's why, I have an old computer from 2009 and it's DDR2. I cannot upgrade its RAM. The processor has the capacity to go more higher, but again, I do not have the RAM slots and the capacity to add more RAM to it. So that limits it, and that will happen. Your processor generally has far more flexing room than you realize, and especially for some things, if you can increase the RAM, you will find, whoa, this processor that I thought was garbage is like, whoa, I got this. That's why many things require dedicated RAM slots. That's why servers have so many RAM slots. So you can't increase it. And RAM is one of those things that are easiest to increase. What's the most common thing people upgrade in their laptop? RAM. What is the most common thing in desktop? RAM. That's why. And if you limit yourself, I'm going to buy DDR4, because be mindful, DDR4 has maxed out. There will not be that much improvement left in DDR4. Prices will come down only a little bit, and only for a short while, because once DDR5 takes over, then it will start to go higher in price. So you will be stuck, and I am stuck. That's how I know. So this is one thing you have to understand. From an investment point of view, especially in long duration point of view, it makes sense just to bite the bullet and buy DDR5, or just wait till January, till AMD Ryzen 5 7000 starts to hit the market. At that point, you can truly make a decision. But almost all the time, it always makes sense to jump the systems, especially for RAM. For everything else, it's like we don't really upgrade. RAM is one of those things that we do upgrade. So that's why it makes sense. And I specified that we could have done ECC properly, even though it would have hit us in benchmarks and all that, is simply because PCI 5.0 is much bigger deal. Why? PCI 5.0 is now reaching reliable throughputs of 63 Gbps. compared to DDR5, 51 Gbps. Let that sink in. RAM is slower than basically PCI 5.0. So that's why when AM5 is released, it has Gen 5 systems. And that's why you will notice, like, direct storage is becoming such a thing. You take the data directly from SSD, bypass the RAM, bypass the processor, just feed that puppy into, GPU, and GPU will decode it. Why the heck that's even feasible, possible? Simply because this is in the pipes. Even for server industry, people are realizing that rather than having, like, terabytes and terabytes of RAM, it's like, what if you just have enough RAM that the processor works and the operating system works and the main tools work, but crunching data is done directly on the SSD. So even if you have a power failure or a fault, you can create a proper trace log, what exactly happened, which bit messed it up, what happened, all that thing. And in case of power loss and all that, all the data is there. In case of crashes, it's all there, and you can recover, redo the rendering engine basically. So in future, the more and more things will be shifted away from RAM to PCI 5.0. It's far more capable system, and that's right now. Like, rather than buying, like, 2 terabytes of ludicrously expensive RAM, you will buy half as ludicrously expensive PCI 5.0 SSDs, server grade one, not the one we have right now, server grade one that can truly touch this sort of speeds. And then you're like, I got this. Because specifically, as I am familiar with VFX works, I used to be a game artist, we know for a fact that for rendering systems, especially if you want to render whole stages, it used to take insane amount of RAM. Like, you could literally have a system that's 128 GB. What we are using it for? Just to render the damn thing, because just to render the AO maps that will bake into the final stage. So sometimes you need GG amounts of RAM. What if instead of using limited RAM, we utilize PCI 5.0? So that's why I said the ECC could have been made into a mainline feature now, because we do have alternate that is ready, that is far more capable, far more scalable. But let's see. But be very mindful. Right now, only Intel CPU is there, and it's very early stage, meaning it has way too many teething issues. It's not that great. And like, type DDR5, and the first thing you'll find, Intel should fix this, as because there was a microcode error where it's like not working properly. And I think that gives AMD a very good chance. They can look at implementation of DDR5 from Intel's point of view, fix out all the error, and they still have till January when they start to mass release this puppy. And at that point in time, they will be like, hopefully this will be better. And not to mention, it was designed from day one to have PCI 5.0 and DDR 5.0, so there is no backwards or compromise or something like that. So we do expect some really good horsepower from DDR 5.0. At that point in time, buying DDR4, not really a good start. Again, if you throw away your computer every 2 years, then it makes sense. But if you are like 3 years, 5 years, 6 years, or you really want to have second use or third use of your computer, yeah, then just buy DDR5, far more usable. So this was my presentation on DDR5. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.